type checking turned off by unsafe. The borrow checker still runs, and most of the things the borrow checker would normally do, it still does. In particular, safe code inside that unsafe block, it'll be checked just like it was before. The borrow checker checks it exactly the same way. It isn't like all of a sudden, unless you just violate lifetimes randomly or anything like that. All these analyses go the way they would before, except you have these 4 things you can do inside an unsafe block. And if you do any of these things inside an unsafe block, so I think I may have mentioned before, we talked about Reddit about what that should have been named, because unsafe is kind of a terrible name. Because it isn't necessarily that it's unsafe, right, what you're doing. If you're almost superhumanly smart and careful, you can write unsafe code that actually is perfectly safe. It's just the compiler can't prove it for you. You have to prove it for yourself. Your code needs to come with a proof. You literally need to paper and pencil prove to yourself that this is going to be okay. That's the right standard for using unsafe. If you made me, I could write down a paper and pencil argument that this code is fine.
Oh, I didn't have a question.
Oh, sorry. All right, so we concluded that I voted for trust me. It's a trust me block because I'm like, yeah, trust me, it's gonna be fine. The internet winner definitely was hold my beer. This is a hold my beer. And that's probably the right way to think about it. Is it's really the hold my beer keyword. And so we're going to talk today about how to use that thing. But let's start with what can go horribly, horribly, horribly wrong. Unsafe, undefined behavior. You'll see all over the Rust documentation and people talking about Rust and blah, blah, blah. The phrase undefined behavior, often just abbreviated as UB, because undefined behavior is quite a mouthful. This is a thing we almost don't worry about in C. Does C have undefined behavior? Oh yes. How do I find out what things in C are undefined behavior? Can cause undefined behavior. How do I find it out? I mean, it's a programming language. There must be a way to find out what it does or doesn't do, what it guarantees you or doesn't. How do I do that? Documentation, the manual, right? I go to the C standard, right? And what words am I looking for in the C standard?
Unsafe.
Undefined behavior. I will literally see in thousands of places in the C standard, the results of this are undefined. Now it turns out that's a strong statement, right? There's a weaker statement that it makes sometimes, which is the results of this are implementation dependent. Which says that, different implementations might do things this way or that way, but they all do it somehow. Undefined behavior is a really strong statement. So in the old days, and I think it's still true, the pragma keyword was added to C. Pragma was a thing that that told the compiler to do stuff that wasn't part of the language definition. That's what it does. And one of the things in the C standard when it went in was, really pragma means undefined behavior. It's undefined what the compiler will do with a pragma. Or implementation dependent, I don't even remember which. And Richard Stallman hated that. He thought it was a dumb addition to the language. And so he hacked up GCC so that every time you used a pragma, it would start a game of Road. Because, when you program ran, it would start a game of Road. Because after all, that's one of the things the compiler's allowed to do when you use a pragma. It says implementation dependent or undefined right on the tin. That's a very Stallmanist thing to do. And we all had a good laugh and then ripped it out. But the thing is, literally undefined behavior means anything can happen. You dereference a null pointer in Rust, and technically it is perfectly legal behavior for the program to erase your disk. And that's true in C too. And the difference is that in C, you get a lot of disks erased over the years. So this is a really, really bad thing. You don't know what will happen. Right? Maybe nothing bad will happen. Maybe exactly what you expected to happen will in fact happen. Here's the bad secret. Modern processors are creepy. They do all kinds of clever things to take advantage of, to try to make things go faster by taking advantage of restrictions. So, yeah, we might, wait to update something in your cache until you actually, read it or put a fence in or something, right? Oh, well, you change on another core. Oh yeah, we don't necessarily show you that value when you do a read right now. You have to do special things to make it happen. That's part of the Intel architecture. Well, that's kind of scary. And so which value do you get? Well, it's undefined unless you make special arrangements for it not to. And undefined can literally mean undefined. Oh yeah, the compiler shows you a random value, the processor shows you a random value, the processor just crashes when you try to read that thing. Processor shows you some stale value. Rust safe subset works with LLVM very closely to try to prevent. By the way, most of Rust's safety bugs are LLVM bugs. And because LLVMs are giant pile of terrible C++. But Rust works pretty closely with LLVM to try to guarantee that all the things you have to do to get defined behavior actually happen under the hood. And at the point where you start just doing stuff, dereferencing random pointers and stuff, Rust is not checking that for you. It's like, okay, I assume you know what you're doing. I assume you understand how fences work on the x86 architecture, 64 architecture. It's like, what's a fence? Well, then maybe we shouldn't be writing something. We should talk. So I'm going to make this very scary. Here's some of the things you can do that will cause undefined behavior. If you ever read a memory location that has not been previously guaranteed initialized, that is undefined behavior. Notice what I didn't say there. I didn't say that returns an undefined value, which is what you might expect the answer is, right? Surely when I read from an uninitialized memory location, some value will come out. Nope. Nope, that's not guaranteed. And in fact, with LLVM and modern processors, the LLVM will optimize a way to read sometimes. And so your code just won't do what you thought. It will decide, oh yeah, you read from an initialized memory, that looks like dead code to me. There was a recent nice blog post by Ralph Levin about this. The LLVM's like, oh yeah, you read from an uninitialized value, I can prove it. Well, it's undefined behavior. I'll just mark the code that did that dead because you're not allowed to read from an uninitialized memory location. Now a big part of your program just disappears and doesn't run. You can't read from an uninitialized memory, it's undefined behavior. Are we clear here? All right. You can't create invalid primitive values, including null references or boxes. So, is 0 a value that could somehow get into a reference? Yes, in unsafe code, it's pretty easy to get there. That's a null pointer. That's illegal. You can't make one of those. Literally just making it, even if you don't ever do anything with it, it's against the rules. And your program can do arbitrary things. This is a big deal. You can't make bool values that are not either 0 or 1. Is that easy to do in unsafe code? Absolutely. Is it legal? No. The compiler assumes that bool values are either 0 or 1. If your bool is 2, this isn't C. If your bool is 2, that doesn't mean true. That means that's a broken bool. Go away. Enum values with bogus discriminants, char values that are not Unicode code points. You can't just have any 32-bit number in your char. Your char has to contain a legal Unicode character. If it doesn't, that's undefined behavior, and your program's literally allowed to play rogue or erase your disk. It won't play with it. It won't play with it, erase your disk. But it might do other weird things you never, ever expected. It might do anything! Or it might just work fine. You don't know. You can't have stir values that are not UTF-8. You can't violate the lifetime or sharing rules with references. You can do that inside unsafe code if you do it the right way, and that would be undefined behavior. You can't dereference a bogus pointer. You can't have a data race. You can't unwind across FFI calls. What the heck does that mean? It has to do with what happens when your code panics, when your FFI, when the function you're calling, for your C function aborts, then what happens? You can't violate the contracts of library functions. If you do any of these things, who knows what will happen? So we're now in a scary, scary place. And we need to deal with the scary, scary place we're in. And here's the right answer to this scary place. Like I say, you really effectively want to prove that things are going to be okay. Anytime I see the keyword unsafe on a function or a block, the thing I expect to see immediately above that is a comment, preferably a dot comment for functions. It describes, this is why this is unsafe. These are the conditions, this is how I can prove, this is for a function, this is how you can call it so that it's safe to use. For a block, this is how I can prove that no matter how this block is entered, it's safe, there's no undefined behavior in this block. All that stuff needs to be written down. You're not going to just assume the reader will figure it out. And if you do just assume the reader will figure it out, a whole bunch of people on the internet are going to get mad at you if they ever see your code. Because these are hard to figure out, and you're probably wrong. The history of unsafe blocks shows that more of them than not, there's undefined behavior in there. And so it's super scary when you see one. And we have to think really carefully about it. Let's look at an example. We're running out of time. I knew we'd run out of time. That's all right. Like I say, we'll finish unsafe on Monday. Here's standard stir from UTF-8 unchecked. Converts a slice of bytes to a string with slice without checking that the string contains valid UTF-8. And there is a safe version from UTF-8. What do you think's the deal with from UTF-8? What do you think it returns as its result type? An option or result, right? Turns out in this case it returns a result, indicating what happened, a UTF-8 error. And UTF-8 error says why it couldn't convert it. Errors that can occur, blah. So yeah. So there's from UTF-8, nice safe function. Why wouldn't I want to use from UTF-8? Why do I even want from UTF-8 unchecked of all the crazy things? I've got these bytes, and I want to turn them into a string, into a stir inside Rust. I want to treat them as I believe that they are bytes of Unicode, and I want to treat them as a stir. That's what this function does. What does the checked version do? What does the unchecked version do?
Checked version makes sure
Make sure
all valid.
the bytes constitute a valid Unicode string. How does it do that?
Make sure that they're not in the range of.
It walks over each byte, right, and says, is this the next byte in a valid Unicode string, right? Remember, UTF-8 is a compressed encoding, right? So it has to look at the first byte and see whether it looks like the start of a Unicode character. If it is, it checks to make sure the following bytes are the right format. And it keeps doing that, right? So it walks over the entire string going, oh, yeah, that looks like Unicode, I'll return OK. Or, yeah, no. I'm going to return an error right here because that isn't UTF-8 at all. Yeah? So why would I want a UTF-8 unchecked? Speed, it's expensive, right? There's no other reason in the whole world not to call the checked version except because you know that those bytes are UTF-8 by some process that who knows what it is. And so why would you ever need to check it? I already checked it. I can prove to myself with pencil and paper that I will never get to this call without those bytes being valid UTF-8, so the check is pointless, so leave the check out. And so it's an unsafe function from UTF-8 unchecked is, and so to call it, I have to call it from inside an unsafe block. So if I want to call this, I literally say, and I'll show it, it's right here, unsafe. This thing, we know it's a valid UTF-8. How do we know it's valid UTF-8? Because we constructed it by hand, and we're pretty confident that we constructed it by hand correctly, right? If I screwed up, I'm never going to know, but I think I got this sparkle heart right. Sparkle heart. And so I'm like, oh, I already know. I don't need to check this. From UTF-8 unchecked. Hold by beer. Right? Yeah. Just treat this as a UTF-8 now. It's fine. Everything's cool. Notice that the only thing that has to be surrounded unsafe is the call itself, right? The result is a stir. The stir's perfectly safe. There's nothing unsafe about it, right? If you trust the code that produced it, yeah, fine. You're good to go. Yeah? Yeah? So that is an example of how you use unsafe. You say, well, I can prove that things are all right. I'm going to call this, and the only thing I don't like about this code is that right above that unsafe block should be a comment. And the comment should say, this call is safe because I constructed the Unicode correctly by hand above. And I'm uncomfortable without that comment, because I don't know why the author thought this thing was safe. I mean, I do if I think about it for 12 seconds in this case, but it should just always be there. You should get in a habit. Every time you say, hold by beer, you explain what you're doing. Yeah? Okay. So that's calling an unsafe function. The other stuff all works kind of the same way. I mentioned raw pointers. So it turns out that for some type T, you can say pointer const T or pointer mut T. And those are like references. They're pointers. Except these pointers are literally unchecked. The compiler's like, yeah, whatever you want to put in this pointer, sure, put it in there. Can you cast a number to one of those kind of pointers and then store it in there? Yes, you can. It's perfectly legal. Can I, do arbitrary additions and subtractions to those pointers? Well, yes, I can. It's perfectly legal. And I can do all that in safe code. Nobody prevents you from constructing any wacky pointer you want to in safe code. It's absolutely legal part of the language. The one thing you can't do in safe code, the one thing you have to say hold my beer before you do, is dereference those. Access where the pointer's pointing. Because who knows how that got constructed, right? It could point anywhere. And it's undefined behavior for it to point anywhere except a certain small set of legal places, and if you dereference it when it points anywhere else, well, sorry. Who knows what will happen. So you have to just run an unsafe block. If you look in standard pointer and standard mem, you'll find a whole bunch of unsafe functions and safe functions for dealing with raw pointers. And those are the ways you're supposed to deal with raw pointers so that they're semi-safe. Highly recommend looking at those if you use raw pointers at all. Notice that a raw pointer is just a pointer. It doesn't own anything. The borrow checker has no idea where this thing's pointing, and it doesn't care. It ignores them altogether, right? So if my pointer happens to be pointing at, some mutex, that doesn't mean the mutex locked. It doesn't, when I point at a ref cell, it doesn't increase the ref count. The borrow checker's like, I don't know, that's just a pointer. I don't know what those mean. Yeah? Yeah, you can absolutely cast the pointers unsafely back to a reference. One of the unsafe operations you're allowed to do is say, no, this isn't really a pointer. This is a reference. That's legal in unsafe code. Again, hold my beer. Better be pointing somewhere a reference could have legally pointed, or it's undefined behavior. Oh, also, when you cast back, the borrow checker's been keeping no track of where this pointer's pointing. It has no idea, so it has to pick a lifetime for your pointer. for your reference. It picks static. It's like, oh, as far as I know, this points to something that'll be around forever. Ooh, that's pretty dangerous, right? I would argue that the default lifetime should have been the empty lifetime, but it isn't. So, so that reference you get back, the compiler assumes that that pointer will never dangle. Your unsafe code better either cast it to some kind of pointer that has a shorter lifetime, or it better make sure it never dangles, right? Or else undefined behavior. That's part of the contract in your hold on beer block. Yeah? Okay. I have a really cool example that I want to show you, which is a modified version of an example from the textbook. And I was all set to spend 20 minutes messing with that example, and we ran out of minutes because that's how things go. So on Monday, we will finish up that example and talk a little more about unsafe code. And then we'll race through declarative macros. We're not going to do procedural macros in this course. And then we'll be done with the course content. It'll be all done. We'll be done with it. Wow. It's been a whirlwind ride, hasn't it? Finish up your projects. Like I say, Wednesday next week is going to be presentations of anybody who wants to present. I hope we'll have enough people to keep everybody busy for a couple hours showing off their stuff. Please consider presenting your project. When in doubt, present. That's my advice. You want to see your cool stuff. Yeah? I'll set up a slide. See y'all on Monday.